So good afternoon. Today I'm going to talk about our work on detecting thousands of 2D and 3D objects using single example training. So as you're well aware, that we are today living in the age of big data. So for many computer vision applications, we have large data sets like Pascal and ImageNet for object detection and recognition. We have Microsoft Coco for semantic segmentation, or for instance, MPAI for human body pose estimation. So all of these data sets have a lot of examples per category of interest, hundreds to thousands of examples. And the solution of choice is usually based on some deep learning technique achieving great results and nice generalization in practice. However, I would like to argue that in many non-less interesting cases, we are still very limited in terms of training that we can use. For example, consider the problem of retail product recognition. There, we usually have to rely on a single studio image per product, which is, let's say, downloaded from the retailer website. And we, in the test time, when we actually use our system, we have to be able to recognize thousands or maybe tens of thousands of products simultaneously from images of shelves of some supermarket. That's the numbers you get when you go to the supermarket. Thousands of products at the same time. So this is one example. Another example is industrial object recognition. There you have maybe several examples for each machine you want to recognize, but they're usually also interested in detecting the viewing orientation of the camera with respect to the object. And then, again, if you pair object plus viewing direction, then you usually get one or most likely 0 examples for all the viewing directions you'd like to recognize. And the third example I would like to focus on is the point cloud pose estimation problem. There you get an image from some camera looking at some portion of the modeled environment, and you want to infer the pose with respect to some point cloud coordinate system out of this single 2D image. So there again, you have only a sparse set of views, maybe a set of images from which you reconstructed the point cloud in the first place using the structure for motion, let's say, maybe up to 100 images, and then you want to detect in completely unseen poses. So I hope I convinced you that this working with okay, good, it's working. I hope I convinced you that this problem of recognizing under very limited training data is important. So before I go into the technical details, I would like to give some motivation in terms of why is it interesting for us. So one of the main focuses of our group is producing augmented reality applications for our clients. And our goal is to make them as more natural and robust and scalable as possible. And of course, we deal a lot with all this problem of massive object recognition or pose estimation with respect to the point cloud, which is usually our model of the world, based on which we generate our augmentation of the physical world. And of course, we deal with some ways to provide natural interaction to the user. For instance, if the AR system is sitting on your smart glasses, the see-through smart glasses that you would commonly use for AR, then the most natural way to interact with the system would be using your hands and fingers. So we work on that as well, but I won't cover this during this talk. And of course, generating all this technology is not enough. We have to package it into real working applications. So here in this corner, you see a video captured from an actual mobile device running our application in real time. This combines both the recognition of point clouds that I'll talk about with the markerless 3D tracking and generating a robust and nicely looking AR experience for the user. You see all these objects tracked and annotations showing where are more interesting objects in the image. And all this is done in real time on a mobile device. So having this motivation, let's go into some more technical details. So I already introduced the technical challenge of product recognition with potentially thousands of objects needed to be recognized simultaneously, and very limited training based on quite unrealistic studio images taking an ideal condition with some ideal lighting, which you, of course, naturally don't observe in the images of the shelves that you take. And given this for training, we'd like to get some, natural training image, natural query image of the shelf, and then I'd be able to recognize the product. So here you see some bounding boxes of the products we recognized, and the actual class that we detected for each bounding box is shown with, with the picture of this single exemplar that we have per product. And of course, this is just one example. We'll see a lot more in the next slides. And the second technical challenge, as I mentioned, the 3 point cloud pose estimation from a single image. There we usually have our point cloud is usually accompanied by a set of training images. There are not a lot, up to 100 maybe training images that were generated together with the point cloud when we reconstructed from the structure for motion. And in these images, the pose with respect to the point cloud is known, and also we know what are the visible points from the point cloud on those images, and they are, of course, aligned to the 3D points in the point cloud. And our goal is, given some 2D image showing this small portion of the scene, to simultaneously detect what are we looking at and align the point cloud to this image. And here you see some alignment result. We'll see, of course, a lot more in the next slides, but just to understand what we are looking at, the query image is shown in gray, and all the color comes from the point cloud that we reconstructed. So here you see that the alignment is quite accurate. This is a general overview of the flow of our approach. We start with the query image. We compute a set of dense descriptors on a regular grid. Then, using those descriptors, we estimate a posterior for what we call task-specific objectness, which are just generating object hypotheses, but disregarding their class. So we essentially generate bounding boxes of objects with the location and scale on the query image, regardless of the class. This is task-specific because we are only concerned in those objects that we want to detect. For instance, in the retail domain, we would want to generate hypotheses only for the objects in this set of thousands that we have, and not some generic object proposals that are used in some other methods. So having this hypothesis, we proceed with the straightforward classification step, where we reuse again the same descriptors, and the conditional probabilities I'll immediately discuss, in order to compute a short list of most likely classifications for each bounding box. And then we do another refinement step, where we again recompute the bounding box based on the detected class, the class that we decided upon. And finally, we have an additional step of deep CNN refinement, where we produce a better fine-grained classification results, because, for instance, in the retail domain, the problem is inherently fine-grained. You have a lot of products which are very similar to one another, like different kinds of shampoo from the same brand and so on. So all the steps up to the deep fine-grained refinement step that uses the deep network are based on inference inside this naive Bayes-like non-parametric probabilistic model. You see this model represented schematically as a graphical model here on the bottom right. So the observed variables in this model are the sampled descriptors, and the unobserved variables are all the stuff that we want to infer, namely the location of the object, its scale, its class, and its relative camera pose for the industrial recognition application. So since I said this is similar to naive Bayes, we assume that all the descriptors are conditionally independent given the unobserved variables. And in addition, in order to be robust to common occurrence of the fact that most objects are small with respect to the image, so most of the descriptors essentially don't have to be explained by the model, because they are coming from the background or other objects, or coming from the object but occur in some occluded regions or deformed regions and so on. We don't have to match the entire object. Essentially, the main property of this model is strong partial matching, which we'll use when we talk about point clouds. So we add an additional unobserved binary variable aj to each descriptor variable fj, which can independently at random disconnect the descriptor from the model and generate it from some background distribution we automatically estimate for the image. So you probably noticed that the proposal space for all the unobserved variable here is quite big. We have 7-dimensional space. Most of the dimensions are continuous. So in order to do efficient inference in this model, we do it sequentially. We break it into first computing the location and scale posterior, out of which we extract the object hypothesis. Then, based on the received hypothesis, we compute the short list of possible classes for each candidate, and then do the refinement step where we fix the class and re-estimate the location scale and where applicable, the camera pose variable with respect to the estimated class. So in order to make it clearer, I would like to run quickly over the inference using some illustrative examples. So here is a query image. These are the dense descriptor that we computed. Here is the objectness posterior, which is a posterior over the location scale. Here I'm integrating it over scale in order not to show a 3D volume. So this is the margin of the posterior on the location. And as you can see, it nicely detects the centers of the object. This marginal is represented here by a heat map with the purple color on top of the greenish image. Now, I'm not going to get into the details of this, but in order to compute this, we of course need to estimate all sorts of conditional probabilities for the descriptors given the unobserved variables. And to achieve this, we use the kernel density estimator, or Parson Windows, if you will, that is computed over a set of approximate nearest neighbors, which we get if we just look for the query descriptors inside the similar computed set of training image descriptors computed over multiple scales. And in order to do the approximate nearest neighbor search efficiently, we use some nice sublinear techniques like the well-known KD trees, locally extensive hashing, seeded expansion, and actually we use them all in order to produce the best results. Having computed the hypotheses, we can back project them onto the descriptors that we sampled, and for every descriptor, compute the amount of support it gave to every hypothesis, so essentially computing the conditional probability of the descriptor given the hypothesis that we're currently examining. And using this back-projected conditional probabilities, we can vote for the most likely class for this hypothesis, and essentially we get a posterior over the class variable. So we're not only getting this short list of most likely classes, but also a full distribution over the possible class. And an additional nice outcome of this, that we can actually map these back-projected conditional probabilities for the descriptors back onto the image, and both get some nice kind of top-down segmentation of the pixels belonging to the object in the image, and also get a mapping between regions of the query image to the training images for the classes that we have detected. And this will be particularly useful when we talk about point clouds. So finally, getting the object, thank you, posterior and the hypothesis and classifying them, we can proceed by refining the location scale, by filtering the descriptors only into those that contributed and to the hypothesis, and also estimating the pose, like in the industrial object recognition you see on the right. So the outcome of this is a set of bounding boxes with classifications, like I said in the bottom left. But in some cases, we have some uncertainty in determining which is the right class between a group of similar products. So in order to alleviate this, we do an additional post-processing step of training a deep network that is trained end-to-end to get this crop of the object we detected, get this posterior of the possible classifications for this object, the full posterior, not the short list, And then we just train it, train this, and we use the architecture of the popular VGGF network with the stride of the first layer reduced by 2 in order to increase resolution and compensate this by additional convolution layer. And the posterior comes in between the 2 fully connected layers and is concatenated for the with the internally generated representation. In order to train this, of course, we can't do it on a single example per class, so we synthesize the data out of these examples, and this is used to improve results. I'll now very, very briefly go over the second application. We can actually straightforward apply this to point cloud estimation problem, pose estimation problem. There, the thing to note is that even if the query image is the most similar training image to it, can be related by a full projective transformation, if we look at sufficiently local regions, they will be still related by some translation and scale. So we can immediately use this because now we have essentially a matching method. We can say that every one of the training images for the point cloud is a class that we want to detect. Use our method to find partial matches, regions on the training images that correspond to the query image, and map the known points from those training images onto the query image to get a set of correspondences between the query image and the point cloud. Essentially, the missing piece is just running your favorite robust optimization method to recover the actual pose, and we use iterative weighted least square. So here's an illustration of how it works. This is the query image. This is the first training image that was matched, and the region automatically matched up to translation and scale, and we copy the black points, the black axes, out of the training image onto the query image, get some correspondences, and this is another training image that matched, and the more correspondences, and more, and more, and more, and eventually we cover our query image with these regions and have a lot of correspondences, and using IRLS, we recover the correct pose. So briefly going over the results. So in terms of product recognition, we have tested our method on various benchmarks existing in our own. I guess the most notable would be the first line here, the Gauzy 3000. Here you can see some examples of images out of this benchmark. I don't know if you can see the obtained classifications, but you have to believe in they are quite accurate. And what's interesting here is that we managed to improve the previously known state-of-the-art by a factor of at least similar to a factor of 2. The previous state-of-the-art is by George et al. From CV14. And another interesting fact is that, I said we have a post-processing step of training a neural network. Why can't we use this same simulated data to train a neural network to do all of this? So essentially try to detect and recognize products on this data set. So we used one of the best deep detectors, the faster RCN by Microsoft Research Asia. And unfortunately, it failed on the task of detecting the full set of 3,000 objects. But we tried it with a reduced set of working with 27 hypercategories. And as you can see, our method performs much better. So, one minute? Okay. So here are some point cloud pose estimation results on 3 videos. Again, the color comes from projecting the point cloud onto the frames of these videos shown in black and white, and in order to illustrate just the power of the recognition, this is done for every frame separately. No temporal integration or smoothing is done, just so you can see the actual results of the recognition on its own. Of course, in the real application, we also do tracking. Here are more examples, and I didn't say, but we're testing on new videos captured with different devices in different times. And here we can see that the car model was captured on a completely different background, but we still managed to make it work despite all the nuisances in the point cloud. Here you see some more examples of the retail product recognition. On the right, you see it applied on the dataset of 4,000 games and videos of GameStop from GameStop retail stores. a lot of videos. This is one of the lines in the benchmark we saw before. So to summarize, I've presented a generic non-parametric approach that can be used for many limited training tasks. I have demonstrated on the retail product recognition, industrial object recognition, and pose estimation for point clouds. We actually use it in real applications for doing AR on mobile devices, like in the video I've explained before. Thank you.